I welcome Vladimir for this amazing podcast where I'm actually trying to demystify what's Kaggle from a grandmaster, what's self-driving technology from a professional who's working there, and as a PhD candidate, he has really seen how this technology also grow because when you are in your doctoral program, you really analyze what is this technology all about. This technology has evolved over a course of time, starting with remote controlling the car to giving an intelligence to a processor. So I'm here to demystify what is a self-driving car with Valdemar. And thank you so much, sir, for giving me this opportunity and filling my bucket list of doing a podcast with a Kaggle Grandmaster.
Okay, thank you for inviting me. Yeah, my name is Vladimir. I got PhD, but not in computer science or like controls. My PhD was in physics.
Yes.
After graduation, I moved to industry and worked as data scientist in a couple startups. And finally, after this, I moved to the company called Lyft. It's a ride-sharing company, but it has a department that is developing self-driving car, and that's where I spent my last 3.5 years. During my closer to the graduation, I learned about Kaggle and I wanted to practice my machine learning knowledge in some kind of intense environment with like many interesting tasks with people, intelligent people with different backgrounds, like kind of collaborating and fighting with me. And Kaggle was the amazing place for this. So I heavily participated for a few years in various Kaggle competitions and finally achieved the title of the Grandmaster. So yeah, in the sense, yeah, that's my background. Thank you for inviting me.
Yeah, let's just jump on to the question. Sir, I want to really ask this one question. How was this journey of Kaggle molded you as an engineer that you are today? Because you have a
Uh,
PhD in physics, which is nowhere related to the self-driving car to some extent. But how has Kaggle really molded you as an engineer today?
there are like few different questions. First of all, Kaggle, I wouldn't say it makes you better engineer in the general sense. At Kaggle, you have really fast iterations, you solve pretty complex problems, you are becoming like really good in analyzing data, visualizing it, you understand all intricacies and details and tips and tricks of all kinds of machine learning algorithms, you are becoming really good in machine learning. And the fact that you spend on competition typically like about 2 weeks or maybe a month, it tells you that like within 2 or 3 years you have like a really like number of problems that you attacked. And this, again, it does makes you good engineer, but it makes your machine learning like knowledge extremely high. I like to think about Kaggle as a weightlifting gym, but for machine learning. Uh, and that's it. So you see, when during your life in the morning you go for in and weight lifts and then you go to work, there is no really direct connection between this weightlifting that you did in the morning versus how efficient, yeah, you are at work. You cannot really like have direct link. But overall, when you weight lift, you're stronger, more confident, you're able to lift heavier weights, and it kind of helps you in your life, like small detail here and there, and sometimes it's more important. Kaggle in some sense does in a similar way. You understand machine learning, you know, don't just, you feel it. So when at work, and it can be like self-driving or can be medical imaging or can be something else, you understand this machine learning so deep that when you add your software engineering skills, your product skills, your understanding of how business works, it it makes you maybe not superhuman, but it gives you an edge over all your all your colleagues, and this is extremely valuable. And in this sense, Kaggle and its experience in all this like different computer vision and tabular data and other types of the competition, it was a big help, big boost for me when I joined Leaf to do self-driving. Because sure, maybe machine learning for self-driving is slightly different than Kaggle, and format of the tasks and way that you collaborate with other people is different, but still this deep knowledge of machine learning that you obtained at Kaggle, it's extremely handy.
Yeah, you told about how handy was Kaggle, but like how handy was your physics, the knowledge of physics which you had prior to joining the industry?
Okay,
every industry person thinks every problem statement by giving an approach in physics. So how has it been helpful in order for you to be that one person who can really work on algorithms,
s-
irrespective of the physics?
okay, so let's just like, yeah, let me answer the question, how physics, got really helpful in this. First of all, if you looked at just, list all this, let's say Kaggle grandmasters in front of you and look at their education, the number of physics of people who have like physics background is disproportionately high. So it looks like there is a correlation between physics background and being good at Kaggle, being good in solving machine learning problems. And I believe it's the case. First of all, physics gives you a pretty strong math background. That's why all these papers, they become like pretty easy like to read. And in some sense, with respect to physics, machine learning, its math is on a very like kind of kindergarten level. Hopefully, like in few like years or decades, it will catch up with physics. But like machine learning right now, it's high school, maybe like freshman year of college physics, like nothing that heavy. So math helps. Also, in physics, it's one of the sciences where you have real life and you have theories, and they don't match. And all your academic career, you maneuver between real life, some real data, and these theories that describe this data, and you need to maneuver in such an intelligent way that it shouldn't look like bullshit. Machine learning in many ways is very similar. You have data, and every like data set that you're using, even if they're very similar, still slightly different algorithms like work, slightly different theory is kind of like applied. That's why this ability to maneuver between like real data and theoretical results, eh, being able to maneuver, have intuition how to do it, and do it in more or less rigorous way. This what physics helps when people move to machine learning, and that's why for people that moving from physics to machine learning, it's typically really straightforward. It's one thing. And this, so physics helped me to become good in machine learning, and being good in machine learning helped me when I joined self-driving.
Yes, you told about your journey as an PhD in physics to the engineers working on a self-driving car. Over the course of time, you should have had come across something called as this problem should have been solved. What are all those canonical problems that are yet to be solved in self-driving car?
uh, you see, machine learning, it's pretty new area, and it's like Wild West in many ways. So people tend to ask, okay, let's think about computer vision, which problems are solved? No problems are solved. Some problems we can like deal with slightly better, let's say classification, maybe object detection, segmentation. Others like much worse, but none of them is solved. For example, for computer vision, stack looks slightly like this. First of all HD cars, all self-driving cars that are shooting for level 4. And here I'm excluding Tesla and Com.ai, but I'm including Waymo, Yandex, Cruise, Lyft, Uber, Aurora, Zoox, and everyone else. They have a nearly identical stack, and that's why when people ask me, could you please tell me about self-driving like stack at Lyft? I typically answer, look for any other company, how they do it, and most likely Lyft does exactly the same. So it helps me to avoid sharing confidential information. So the stack, general stack for this level 4 for all these car companies, excluding Oma and Tesla, looks like first we build HD map, high definition centimeter quality like map, like in 3D in GTA if you want to think. And then car is driving on the roads, identifies where it is on this map, and it tries to identify where are the locations of different agents. And by agents, we mean animals, pedestrians, cars, trucks, emergency vehicles, police vehicles, something that is moving. And this is perception task. For sure, perception is operating in the domain of computer vision, of course, because cameras is like very like cheap and dense source of information, and lidar, so to identify in 3D, to do this. So they're like a set of algorithms in computer vision, and they're more or less working, like as I said, classification, object detection, segmentation, and images. As you know, you open any like conference and like bunch of papers and pretty good results. But these results are good, but they may be good for many different applications. But in self-driving car, due to the fact that the price of the mistake is really high, let's say you don't, and you remember this case with Uber, they didn't detect properly and didn't classify this bicyclist, and they killed the person, and it was bad for the industry, bad for the person, bad for the whole family of this person, and no one wants to do it again. And that's why even 99% accuracy is just not enough. So problems for all these algorithms technically looks like we could solve them long ago, because ImageNet is pretty like high accuracy, but this problem is not solved yet. If we are looking for areas of machine learning that is less developed in the industry or even in academia, its next step would be machine learning on the LiDAR point clouds. Overall, not that many tasks that really require like working in 3D on point clouds. It can be something in medical imaging when you do like 3D scans of the body. And let's say it is this like LiDAR point clouds for self-driving. And that's why for many years, academic community, they just didn't have access to these algorithms. For many years, people worked with Kitty dataset, which is pretty small, and only in the past few years, Waymo, Lyft, and different other companies, they're releasing more and more data sets, and it automatically boosted the performance of the algorithms because more and more eyes are looking at this, but they still suck pretty much. They're okay, but not good enough to just to send it in an automatic way to the road. And then comes even less established area when we're talking about planning and prediction. At any moment of time, even if we identify who is like where on the map around us, and we understand how they moved in the past, I don't know, like 10 seconds, we need to predict what they will do next. We don't know how to solve this problem well. Lyft hosted competition at Kaggle about this. I was one of the hosts, and results were pretty impressive, but still there's a long road there. So that's where low-hanging fruits and a lot of impact hangs. And also planning, like even if you understand how like everyone is moving around you, what exactly should you do? How you should maneuver in all this complex environment. Right now, self-driving companies, they're trying to operate in relatively like free of agents. Like Waymo is operating in the self-driving mode, trying to operate in Phoenix. And Phoenix, for those who have been there, is really empty city, no pedestrians, extremely rare, so kind of easy task. But let's say if you take this car and move it to the center of, I don't know, San Francisco or New York or Los Angeles, or maybe somewhere in India or in Russia, this car will get stuck instantly. And this means that like all machine learning algorithms are, I wouldn't say immature, but there's like a long way to go for people who are working there to just master, to improve it. And that's why they're actively hiring new people, skilled people, or they're monitoring all conferences for the best results, trying to get an edge here and there. But in reality, so far, everyone is doing nearly the same. Some companies slightly better, some companies slightly worse. And all algorithms, you may say, I don't know, object detection, like working well, it should be closed long ago. Still not yet. Not to the accuracy that we need for fully operational, safe, self-driving cars.
Yeah, you told about how the problems are not being solved. You also told about how we have to try to identify new problem statements somehow or the other, because each and every domain has its own different story. But as as a professional, you have seen various different roles. You have dealt with different amount of people. You have dealt with different people with different approaches. But I want to ask you this one specific question, because most of our research, let me just say, we are working on action prediction. For our research, we use autoencoders, variational autoencoders to some extent, and then we go back to the GAN saying that, okay, all these are the old algorithms, what do we want to do? So now we go with the GANs, and something else keeps rolling in and out. But I want to ask you this one question specifically, because many questions can be answered through this. I want to ask you, which is the most hardest part of a self-driving car? Not a component, but I'm talking in terms of technology that is involved in this self-driving car technology.
You mean technology, mean in the algorithmic sense?
Algorithmic sense, and also in terms of sensor suits, also in terms of planning and what you said, because for the planning, it
Okay,
can
I
be
would
anything.
say, okay, problems are everywhere. First of all, like no part of the self-driving stack is solved. Some are slightly better, as I've said, prediction and maybe HD maps, like others maybe slightly worse, but nothing is solved yet, and people are required for all of them. But probably the biggest blocker that I feel self-driving technology has right now is prediction and planning. And these problems are not to the lack of the data, and these problems are not to the fact that I don't know, like our neural networks are small enough. Problem lies in the scientific field. We just don't know how to ask this question properly. We don't know what type of neural network should be used to process this data. We don't understand what representation this input data should have. So it's not about let's train heavier model and throw more data. It's more about what should we do, how should we approach it. And so this is in many ways purely scientific problem. I've heard people sometimes ask, is it true that legal limitations of the legal system in different countries is the biggest blocker to the self-driving technology? My answer is no. It's the least of your there are some problems, but it's the least of your problem. The biggest problem is not even engineering. It's exactly scientific. We and here I mean as a humanity didn't figure out yet how to solve the problem of prediction and planning in a scalable, reliable way. There was a hope for deep reinforcement learning because in theory this technology could help to address these prediction planning issues. No one figured out how to use it outside of some simple cases in something that's more realistic. That's why this is like the hardest open question in the self-driving technology, to my knowledge.
How close are we to getting the level 5 and the level 4 autonomy to the world tomorrow?
Uh, I don't know. It's really hard to say. If our problem was legal or maybe engineering or something else, we could have like good estimates. But because problem is in the scientific domain and we need a few scientific breakthroughs, and scientific breakthroughs is pretty hard to plan. They may happen tomorrow and they may not happen in the next couple hundred years. I don't know, level 4 autonomy. So optimistically, people think that by the year 2025, so in 5 years, we'll have level 4 autonomy. More realistic, I don't know, go for 50, 70, 100 years. I'm talking about level 4. Level 5 so far, based on what we know about self-driving, it is science fiction. You just don't use level 4. You just, okay, let's get to it when we get to level. Let's talk about level 5 when we get to level 4, and to level 4 we may get, I don't know, in 100 years, if we are lucky.
Yeah, I was thinking of, there are connected cars today. Cars are just being communicating with it. Somehow Tesla is also collecting data from its drivers.
Mhm.
I was thinking of, why can't we have a connected driver? Means, why can't the sensor suit be on a human being and take the decisions from the human being, take it as a feedback, work on it?
It, it is possible way to this, but imagine in your home city how realistic it is that everyone will wear such a sensors. They will work without problems. People will not try to break them. No one will try to hug them. And each sensor and operating this network is so cheap that it allows this whole self-driving cars and network to be profitable. You see, in theory, it is possible. In practice, it's pretty hard for me to imagine.
Yeah, when we are talking about connected cars and the connected drivers, I was thinking of, like, Lyft has been that one company which has set that gold standard for the data sets. Any Kaggle competition, Weibo and Lyft, there's a competition between them. I love Lyft data set, man.
Mhm.
I just want to ask you this one question. What kind of a data set will we be seeing in the tomorrow's world? Is it like pre-processed by a neural network, then given to the source, or else what is the nature of the data that we might be seeing tomorrow with respect to the data that we are seeing today on the self-driving car?
So I believe that the biggest chunk of the data that we see on self-driving car tomorrow will be pretty similar to what we see today. Again, it's data from cameras, from radars, lidars, HD map, maybe some extra information. Imagine that, let's say we install some Bluetooth transmitters in every traffic light, and they will just, when car drives close to them, they will also like transmit the signal. So this type of the additional signal could be possible. Again, as you mentioned, let's have like a sensor on every person and they will like emit something. Maybe this, but they look pretty small and less important than this major bulk of the data that is already kind of like, that all the cars are generating: camera, lidars, radars, these accelerometers, and maps. So far it looks the biggest chunk. Maybe if some company or maybe some researchers will come up with, okay, let's look at this problem in a different way, and if we add this essential source of the data, the picture will change and many problems will become solved, sure. But so far I and probably others, we don't see like this source of the data that is so powerful that will allow to solve some open question that we have right now. But yeah, I agree, like transmitters in different traffic lights and traffic signs, and maybe transmitters and different people, or maybe if all cars in the city would communicate to some central network, all this like information about them, and this will kind of like allow them. Just imagine there's like dark and two cars are moving, they don't see each other, but if they communicate to some central source, this, source on the server, it can visualize these two cars and tell them, okay, like move right, left, and even these two cars don't see each other, they can avoid collision. Possible, but plenty of problems there.
Yes, sir. I just want to ask you this question on the most impactful breakthrough that this industry has seen. And also, you can say the most impactful breakthrough that you have witnessed in your studies throughout as a professional, as a student. Like, I just want to ask you this question, like, what really led this technology to have such a boom overnight? Not overnight, it had a lot of years of development, but like what really was that most important breakthrough in this technology today?
I mean, probably there are plenty of interesting breakthroughs, and let's say I believe that in the long-term perspective, AlphaGo and like way AlphaGo Zero, way how DeepMind was able to train such a network to such a, like an impressive results without, for games that was strongly believed that couldn't be attacked algorithmically because they're too complex, like Go. Mm, And this has a lot of impact, as I understand, on the way that people think about what's possible, what is not. But in terms of practical applications, probably it's still this ImageNet 2012, when people showed how neural networks trained on GPUs, convolutional neural networks, how without like building like complex heuristics, tuning like some crazy hyperparameters, as was done in all traditional computer vision, you can just like throw more data and solve problems. This new way of thinking of programming, and Andrei Karpathy called it like programming 2.0, when throwing more data can help you to improve the quality of the programs. People before this, people never thought about this. It didn't cross minds of many people in industry, and right now it is basically a baseline. Everyone talks about data, more data, models with more capacity, and just think about this. If you take your cell phones, it's just like full of the technologies that are based on this. And if you think, sure, 2012 was the ImageNet, then for the next couple of years, it was not well recognized outside of the academia, but then slowly it started propagating to the industry. And probably, as I remember, it was yet 2017 when companies in Silicon Valley started aggressively like hiring people for computer vision. So think like from 2012 to 2015, it's only 5 years. Typically in industry, from some development, some invention to the innovation. So when this invention starts making money and becomes popular and starts a new wave of industry and all these companies trying to ride this wave, 5 years, it was a really small period of time. And this talks about the power of this result. So from theoretical point of view, I would say this AlphaGo zero, but from way that industry changed and services that we are like have today and enjoying today, it's this ImageNet 2012.
When we talk about deploying a models at a very large scale,
Mhm.
self-driving car technology has multiple models, multiple parameters to consider at every given point of time. How different is deploying at a scale different from deploying a model from a Kaggle competition?
Uh, so let me answer this. So yeah, deploying models. I mean, first of all, there's a lot of similarities. Like deploy is deploy regardless of it. And so many things, they are just pretty common. At the same time, car, it has limitations on how fast does it work. So in the sense, deploying to the car has similarities also to deploying to the edge devices, mobile phones and others, where it just should work in real time. Plus, so yeah, because it should work in real time, you have a lot of limitations on the performance and a lot of optimizations happen on the models to make them lighter, faster, to have models faster, pre-processing pipeline, everything to do faster. And this again, pretty like similar to mobile devices with of course its own specifics, because amount of the data that is flowing through the self-driving car, we're talking about lidar and radar and like multiple cameras. It's all pretty heavy and should be kind of like done well. That's why for every company that is starting like their self-driving efforts and people are joining them and they're promised, okay guys, you build machine learning engineers, you work on this like cool algorithms, what is happening for the first like 2-3 years? Instead of training models, they train models, I don't know, like once in 6 months, and all the rest of the time they're building infrastructure, how to deploy at scale, how to deploy it fast, how to like make versioning, logging, debugging kind of automatic. And also like for many self-driving cars, many companies, they are exploring a thing called late fusion. So what is the late fusion? What is early fusion? Think about this. Early fusion, it's, let's say you have data coming from cameras, you use neural networks to extract some high level information of bounding boxes from these cameras, and then you combine this information kind of like in some heuristics or maybe fit to another, or add some output, some detections from the lidar, and then you combine all of them together, and this is output. So it is early fusion. You processing like different sources independently and then combine it, and this goes well. It has its limitation, and that's why, let's say, if you watched the talk by Andrei Karpathy about how they do in Tesla, they're doing late fusion. So it's a huge network that takes multiple sources at the same time, extracts this high-level information in these abstract representations, and then like some common head of the network or like set of heads, it's just doing something. Just training this enormous late fusion type behemoths, which are like pretty huge and heavy and hard to train, it required special efforts. At Kaggle and in other like more simplified environments, you just don't face these problems.
Yes, I just want to end this podcast with last two questions because I'm enjoying it, but I don't want to send you because all my questions, all my doubts about the self-driving technology is getting solved. Like last two questions. One question is like, how's the public perception over the self-driving car? I'm talking in terms of the car being accepted in the public tomorrow, and how hype or how much is the hope that self-driving cars will be the next new normal. And also I want to ask you that one most beautiful concept that you have come across in any of the subjects that you have come, let it be physics, deep learning, mathematics, anything.
Beautiful concept. Yeah, you're
Yes,
saying. Okay,
the
let me
most
think.
beautiful
Okay,
concept you have come across in your life.
okay. So let's like answer first question about public perception. So what's happening right now? Many people think that companies are doing some small testing in some limited areas, and we don't have estimate of what does public think about this. It is not the case. The reason for this is that, let's say, a company called Motional is, for the last like 3 years, they are providing self-driving service in Las Vegas, and they're using Lyft app for this. So if you're coming to Las Vegas, you open app and say, okay, like, could you please drive me to this, like, place? There is a chance that it will ask if you do you want to do like self-driving, and you say sure, yes, and then this like car of the Motional will come to you. Yes, it will be safety driver, but still it's mimicking the kind of like future experience where this like safety driver will not be there. A car starts moving, like wheel is rotating, and from every this ride, people collect feedback of like what actual like random people who use the service, what did they do. Waymo does similar in Phoenix. Yandex is doing similar, I believe, in Russia. And so there's like some estimate of the public perception. And so far, it looks like it's pretty nice. First reaction that's kind of like unexpected. But then, because it's kind of like actually boring to drive in self-driving car, it doesn't hit anything, it doesn't accelerate like crazy, it just drives you from point A to point B. And my belief that instant self-driving will be ready for large-scale deployment as a product. I think for the first few days it will be some excitement, some shock, or I don't know, maybe some emotions. But within first week, people will just like accept it as it was always there. So no problem of this. I think it will go absolutely smooth. Yep. Okay. The most exciting thing that happened
You
in
have come
what?
across, the concept that you have come across, the most beautiful concept that we have come across, let it be in any subject that you have read.
You see, this is like pretty tricky. So if I compare just physics to machine learning, physics is significantly more exciting. It's pretty majestic, and it's talking about some really interesting thing in a weird way, like like space that is bending, or like black holes, or something else about this. So self-driving is cool, but it doesn't like make my heart beating faster every day. But thing that I was always excited since childhood is the idea of traveling to another planet, so to another like stars, or even into another galaxies. Something that when you watch Star Wars, you see different planets, different societies, how they interact. Just like, wow, this is cool. I want to live in this place. And that's why when I was studying physics, I was always curious and interested about like traveling to different planets, first within solar system, and then like there. And progress there is not like ultra huge. Still, I'm very excited that like Elon Musk is trying to push this hard with his money and drive and intelligence and everything. And basically, I'm more excited about latest news that, let's say, China is trying to like build moon station in the next like 5-6 years. It's not like, as I said, self-driving in 100. It's like next 5-6 years when we will have so space station first was ultra exciting to me, but when we'll do next step and we have moon station, and hopefully maybe in the next 50 years, hopefully I'll still be alive, and at Mars I'll be the happiest person.
Yeah, thank you so much for this amazing podcast, sir. It made my day and it made my bucket list get filled. Thank you so much.
Okay, thank you for inviting me.